This video is on the objective compute the value of the test statistic using the expected frequencies for a chi-square independence test. Alright, so by now you've seen the chi-square, goodness of fit test, where you determine if a certain distribution fits a given distribution. This test, the chi-square test for independence, is a test to determine whether or not two factors or two variables are independent. Right. And your null hypothesis in each of these tests is going to be that the two variables are independent. The alternative hypothesis will be that they are not independent, they're dependent, and then you go from there. So this video specifically is on determining, the test statistic, the chi-squared test statistic. Alright, so here's a problem I'm looking at. Now again, if you want to see more about the objective, click on More Instruction. And in fact, I'm going to show you some of that instruction right here, instead of writing it all out. Alright, so the test statistic for the chi-square independence test. So like I said, in this type of hypothesis test, we determine if two variables or two factors are independent or dependent. In this case, there will be two qualitative survey questions or experiments, and these tests involve using a contingency table of observed values, right? Remember, the observed values are the actual data values. The test statistic for a test of independence is similar to that of a goodness of fit test. It's calculated in pretty much the same way. Right, your chi-squared sub 0 is a sum, right? And you see the sigma here, you're adding. Now notice they have I and j there. I times j. Right, this I times j is going to tell me how many terms are in the sum. And then again, every term of the sum is some observed number minus some expected number squared divided by the expected number. So again, the O's are the observed values, the E's are the expected values, and they're what you would expect if you assume the variables are independent, right? Because that's going to be the null hypothesis, that you're going to assume that the two variables are independent. I is the number of rows of the contingency table. J is the number of columns of the contingency table. And the test statistic has approximately a chi-square distribution if the null hypothesis is true. And again, this sigma symbol means you're adding. Right? So you're going to sum I times j terms. That's the number of terms you're going to be adding of those observed minus expected squareds divided by expected. As with the goodness of fit test, we're going to be just performing right-tailed tests. Right. The test of independence is always right-tailed because of the calculation of the test statistic. If the expected and observed values are not close together, then the test statistic will be very large and way out in the right tail of the chi-squared distribution, right? Just like in the goodness of fit test. And we'd most likely reject independence. We'd reject the null hypothesis if that were the case. And if the observed and expected values are close together, right, then we'll have a smaller value of this chi-squared test statistic, and it won't be in the rejection region, some right tail. And we would keep independence. We would stick with the null hypothesis. Alright, so they get into here how to calculate these expected frequencies in a contingency table. Right, so I'm going to actually write some stuff out on paper here to show you where this formula comes from. In a chi-square test for independence, the expected frequency for each data cell, right, in the contingency table used in calculating the test statistic can be found by using this formula. So the expected frequency, the expected number in a particular cell on the table, is R times C divided by N, where R is the total for that row, C is the total for that column, and little n is the sample size, the total sample size. Alright, so they give me an example here, which I'll write this out on paper and show you, where this expected count formula is coming from. Okay, so here's what the general contingency table looks like. So you're going to have some categories of a certain variable, one variable over here represented in, broken up into different categories, or one factor, and you're going to have another variable that's represented by these columns and broken up into columns. So you have a row variable and a column variable. And say I have m rows, row 1, row 2, row I, row m, all the way down to row m. And say I have k columns, column 1, column 2, column 3, up to column j, and then after that to column k. And what we're going to do here for most of our contingency tables is create, kind of extend these, where this row after the main data is going to be in these m rows and k columns, and then we're going to have our column totals down this row. So the say C1, that's going to be the total of all the column 1 values, and then C2, and then dot dot dot, and then CJ, right, dot dot dot, and then CK at the end here. Right? Again, this is just the sum of all the values in this column, right? And we'll extend it on the right side as well, and I probably should have left some space here. Let me slide another piece of paper. Alright. We're also going to extend on this side and create a new column with our row totals. Alright, so this will be for row totals. Alright. And the sum of the first row will be, I'll call R1. The sum of the second row I'll call capital R2, right? The sum of all these values in row 2, and so on. And then the row I, say, has R sub I, and all the way down to, say, row M, however many rows there are, row M. Right? And then in the very lower right corner, down here, is the grand total, which is the total sample size. How many people, how many observations total were taken, and this is that lowercase n. So this is the sum of all the row totals, or the sum of all the column totals, right? So all my column totals should add up to n, all my row totals should add up to n, and again, n is just the sum of all the values in the table, right, that aren't column totals and row totals. Alright, so what we're going to be doing, right, is in the null hypothesis for these tests, we're going to be assuming, right, the null hypothesis is we're going to be assuming the two variables are independent, right, this row variable and this column variable. The variables or factors, right? We're going to be assuming that they're independent. Now, hopefully you remember back, it's been a while now since we talked about probability, actually calculating probability of independent events versus dependent events. If I said let's take a look at this cell here, this cell in row I, column J, and I wanted to know what's the expected number, right? This capital E with I'll put subscript ij. So this is row I, column J. What is this? Well, if I assume these variables are independent, how many of these n people would I expect to be in that cell? Have this, be in the row I category of the first variable and the column J category of the second variable. So hopefully you recall how to find probability. Recall that if I want to know what's the probability of being in row I and column J. Well, this is two events. This is a compound event, being in row I and at the same time being in row J. And remember, if these two variables, the row variable and column variable, if they're independent, then this would be equivalent to the probability of being in row I multiplied by the probability of being in column J. And let's think about this, Remember, there are n people total. If I select a person at random, the probability that they're in row I would be the row total for I, right? And they just called it capital R, I'm calling it R sub I, divided by n, right? The number of people in row I divided by the total number of people, multiplied by the probability of being in column J. Again, if I take these n people and select one of them at random, what's the probability that they're in column J? Well, it would be how many people are in column J, right, which I called C sub J, which they're just calling C, divided by n. So here, I have the probability of being in that cell. So remember, probability is like a percentage, right? Probability is a percentage, a fraction, something less than 1. So there were n total people. I'd expect this percentage of n to be in that cell, right? So we would expect in the ith row, jth column cell, there to be this probability, right? The row total, row I total, times the column J total, divided by, n times n. I'm writing it this way for a reason. We'd expect this percentage of our n people. And then you see the n's canceling here, and then this gives us the formula they gave us, right? The expected number of people in a certain cell in our contingency table is the row total times the column total divided by the total number of people, divided by the whole sample size. Right? Okay, so, and then we're going to do this, we would do this for every single cell. Every single cell. And then we would take all the observed data and subtract the corresponding expected data, square those, and then divide by the corresponding expected data, and then add all those up, right? And we do it for every single cell in the table, right? So it's a lot of work here, and I'll show you how to do a shortcut on the calculator, of course. But let's actually get to our problem now. Right. Okay, so here a survey. A survey asks a group of college students about their majors. It also asks it also groups the students by whether they are athletes or not. These values are recorded in the contingency table below. which of the following tables correctly shows the expected values for the chi-square independence test? All right, so I'm going to write this table out. All right, now first I'll write out, without the totals. I'm going to write it without the totals at first. All right, we'll just look at the table itself with the data, and then I'll write the totals. Okay, so right now, these are all the observed values. All right, and I'll label them like this. All right, so this is, the observed value in the first row, first column. So I'll call it 011. And then, so of these students that they surveyed, we have two variables here, right? Two factors. Up here, the variable represented are the majors. Right? What are they majoring in? Arts, humanities, sciences. And then the factor or variable over here is, athlete or not, athlete or not. So we're going to ask the big question, if we were running the full test, we would say, does a student's major, and whether or not that student is an athlete, are those factors independent of one another, or are they related in some way? Okay. So now we have, again, this is all the observed data, what they actually observed in this survey. So 14 of the students they surveyed majored in the arts and also were athletes. 19 students were majored in humanities and were athletes. And I'm going to call this 012, right, because it's in the first row, second column. And 18 students majored in sciences and were athletes, and again I'll call this 013 because it's in the first row, third column. Alright, then 23 students majored in arts and were non-athletes, and I'll call this 02, 1 because it's in the second row, first column. 9 students majored in humanities and were not athletes, and I'll call this observation 022, right, because second row, second column. And finally, 16 students were majoring in the sciences and not athletes. This is 2, 3. All right, so there are 2 rows, right, 3 columns. So when I go to do that test statistic later, I'm going to be adding up 6 different things, right? 2 times 3. Number of rows times the number of columns will give me how many terms are in that sum. Okay. So now come the totals. All right. So down this extra row here, I'm going to do it in a different color, are the column totals. All right. And they've already got them on the table there, but I'll do it here, right? So basically this just tells me how many of the students that were surveyed are in a certain major, right? How many majored in the arts? Well, 37 of them, right? And again, I'll call this C1 for the first column total. How many majored in humanities? 19 and 9, 28. And again, I'll call this C2 for the second column total. And then 44, right, I'm sorry, 34, 18 and 16. 34 of these students majored in sciences. And I'll call this C3. All right. And then down this column, put the row totals. Now these row totals will tell me about, the factor of whether or not a student is an athlete. So how many athletes were surveyed? Well, 14 and 19 is 33, right? Plus 18 is 43, is 51, right? And again, I'll call this R1 for the row total, for the first row. And then the rest of the students were in the second row, the non-athletes, and that's 23 and 9 is 32, plus 16 is 48. Right, so 48 of these students were non-athletes. I'll call this 48R2. And then in the very lower right-hand corner, I've got the grand total. All right. This is N. This is the sample size. This is how many students were surveyed, the total sum of all 6 of these observed cells. Well, you can add up, the athletes and the non-athletes make a total of 99. So there were 99 students. Or you could take, the arts majors and the humanities majors and the science majors and notice that that also adds up to 99. All right. So this is the grand total, the whole sample size. Okay. All right. So what they're asking us for are what are the expected counts. All right. If we assume, all right, so if we assume that a student's major and whether or not they are an athlete are independent. And so if we assume a student's major and whether or not they're an athlete, if we assume that these two factors are independent of one another, then how many of the 99 people would we expect in these 6 spots? Right, again, these are the only 6 that matter. The row totals and column totals I'm not doing this for. Then, how many students would be expected in each cell when n equals 99, right? When you have 99 students, right? So that's the question. All right. So again, I'm doing this 6 times, and I'll pull a calculator up for this. So here's my expected counts table. So we had again the majors, and then whether or not the student was an athlete. And I'll just come back when I'm done making this table. Alright, so I just filled in all the lines here. Alright, and then again, if we're assuming independence and we had a sample of size, 99 here, based on the previous observations, based on the observed table, what would be, say, the expected number of folks to be, majoring in the arts and an athlete at the same time? So again, that's the first row, first column, so I'll call it E11. Well, I showed you the formula for this earlier. This is you take row 1 total from the observed table, multiply by the column 1 total from the observed table, and divide it by the sample size. All right, so going back to my observed table, the row totals and column totals, this would be 51, the first row total, times 37, the first column total, divided by 99. Right. So this is 51 times 37 divided by 99. And I'm going to enter this into a calculator. This won't be a whole number. Right. So let me pull a calculator up. And let's do this. Right, so we have 51 times 37 divided by 99. So about 19.06. Because remember, hopefully you recall expected value, again, back in chapters on probability and probability distributions and all that. Expected values, doesn't mean that because you can't have 19.06 students being in a certain category. This just means in the long run, if I were to do this over and over again, I would expect the average number of students out of 99 that major in the arts and are athletes to be 19.06. Okay. All right. Okay, and then let's do the same thing for the humanities and the athletes. How many students would you expect out of the 99 to major in humanities and be athletes? So that's E, that's first row, second column, so E1, 2. And again, this would be just take the row, that row's total, that column's total from your observed table, and divide by the sample size. So again, 51 for the row total. That second column total was 28. So 51 times 28 divided by 99, right? The sample size. And I do this here. So 51 times 28 divided by 99. So approximately 14.42. So again, these are expected counts here. All right, then for the sciences, again, that would be E1, 3, first row, third column. Again, I take the row 1 total, which we know now to be 51, times the column 3 total from our earlier page, which is 34, and then divide that by 99. So 51 times 34 divided by 99. One more time here, and then I'll fill out the other row, and then without writing it down, and come back to you. 51 times 34 divided by 99. So approximately 17.52 if I go to 2 decimal places again. Right. And then I would do the same for these, but instead of row 1 now I'm in row 2, so I'd use the row 2 total of 48. So I'd be doing all the same calculations, but instead of the 51s, I'd have 48s. Alright, so I'm going to just do that and come back when all this is written up. You'll see it in a flash. Alright, so you see it popped up right there instantly. You might notice on my calculator I did all the 3 calculations are on my calculator here, where again 48 instead of 51. Right, that means in the row 2 for the row 2 totals times the column 1, column 2, column 3 totals, and then all that divided by 99. All right, so what I have here are all the expected counts, right? What if I had a sample of size 99, based on the previous observations, and if I assume the variables were independent, what would I expect my expected counts be in each of these cells? All right, now going back, that's one of these. Let's see, so it was 19.06, so about 19. They went to 1 decimal place. So let's see, 19.1, 14.4, 17.5, 17.9, 13.6, and 16.5. These are the ones. All the expected numbers are underneath the observed numbers on these tables. This is the one that matches, when rounded to 1 decimal place, matches the one I wrote on my paper. Okay. And again, they show you going through all those calculations. Now they only show you for the first row, first column, and I guess you could have just done that because it's multiple choice and the only one that had 19.1 in the first row, first column expected value was the second one, so you could have just done that, but you should be able to do all of them. Now let me show you another way you could have found this as well on your calculator. So again, I'll pull the calculator up. Now, this table, right, the contingency table has 2 rows, 3 columns. Again, you're kind of ignoring the total rows and column, the row totals, the column total. Ignore those. The actual data itself, right, the observed data is the athlete rows up for arts, humanities, and sciences, the non-athlete for arts, humanities, and sciences. This 2 row, 3 column table. So what you can do in your calculator is make a 2-row, 3-column matrix, something called a matrix, which is just a rectangular array of numbers. Some of you may have heard of them, some may not. It doesn't matter, you'll see it here. So on my 84 plus, and this is on the 83 as well, above the x to the negative first button, there's a thing that says matrix. I would hit second, then this inverse button, and it comes to this matrix area, and I want to make a matrix, edit a matrix. And so I go over to edit, and then pick a matrix, these things surrounded by the brackets. I'll say matrix A. Then it asks you for the size of the matrix. Right, now this is the number of rows by the number of columns. So it was 2 rows, 3 columns. All right, then I'll enter the observed counts. So in that first row, first column, there are 14. Right, I'm just entering all the values I'm seeing in this 2 by 3 table over here. First row, second column, 19. First row, third column, 18. Moves you down to the second row, then second row, first column, 23. Second row, second column, 9. Second row, third column, 16. All right, make sure, now get out of here, second, and quit. And now what I'm going to do, all right, you'll see the calculator can make this matrix of expected values, all right, with all the 19.1, 14.4 and all this, all the expected counts for a sample of size 99. It'll do it for you. When you run, now this is kind of getting ahead of ourselves here, but when you run a chi-squared test, so remember how to run tests. You hit stat, hit the stat button, go over to tests, and if you scroll down, now we did the chi-squared GOF test before. All right, that was this one, the GOF test. That was goodness of fit. We're not doing that one this time. We're doing an independence test, right? Just a plain old chi-squared test. So I go up to where it says chi-squared test, hit enter. And then you see it says, what's your observed matrix? You see the thing surrounded by brackets? Now I did enter that in matrix A. So keep that as matrix A, if that's where you put the observed counts. And then, we didn't write down an expected matrix, but we don't have to. It's going to do it for us, and I'll show you. So make sure this expected matrix is, some other letter matrix. This is matrix B here. Go calculate, and now up pops the test statistic, 5.7926. That would be all the observed minus the expected squares divided by the expected added up. And then you got a p-value and a degrees of freedom and all that. Go back to that matrix menu now. After you have run the chi-squared tests, go back to the matrix menu. Go second matrix. And look at this. See how earlier there wasn't a matrix B. Now there is after running the test. And I'll just stick with names here. Go down to matrix B, hit enter. It'll show up on my screen. Hit enter again. You can see the matrix. And look, 19.06 for that first row, first column. Remember, that's the expected value I got when I did it by hand. And scroll right, you see 17.515. Right, that was for the that's the first row, third column. That's exactly what I got in my drawing earlier. The middle one, sorry, I passed up the middle one. 14.42, that's the first row, second column, expected value. And 17.939, which is 17.94. The 13.575. And 16. 13.5757, blah, blah, blah. And then eventually I should see, there we go, keep scrolling right, 16.48. But you're getting all those expected values that I got when I did it on paper. And it just does it for you, right? So you enter a matrix with your observed counts, go to Stat Test, run the chi-squared test, and then go back to the matrix menu and you can see all those expected counts. But it really doesn't matter because when you run the test, you saw it gave me the test statistic, right? Which now let me get into actually calculating the test statistic, by hand here. So going back to paper. Let's get rid of this. All right. So now that I've got these, expected counts written down, got all the observed counts. If you want the test statistic, I already showed you how to find it quickly with the calculator, but if they want, do it by hand. The test statistic, that chi-squared sub 0, is again the sum, and they had the I times j. Well, again, that's just the number of rows by the number of columns. So that just means there's going to be 6 terms in this sum. If you take the number of rows times the number of columns, there'll be 6 terms of this sum. Then you have the observed minus the expected squareds divided by the expecteds. So for this one here, just go for each cell and then their corresponding cell, expected cell. So for the first row, first column, the observed count was 14 minus the expected count was 19.06, and then that's going to be squared and then divided by the expected count, plus, and then I do it for the first row, second column. The observed count was 19. The expected count was 14.42. This gets squared and divided by the expected count, 14.42. Plus, and you would just keep doing this for all 6 cells. And the last one I would do would be this second row, third column would be 16 minus 16.48 squared divided by 16.48. And this should give me my test statistic, which again, I would highly recommend, instead of doing all that, just enter that matrix and go and do the chi-squared test. All right, go to chi-squared test. I already have the observed and expected in, calculate, and this sum here with all this craziness would be approximately 5.79. All right. So I'll tell you right now, use your calculator. It is going to be a lot faster, because this was only a 2 by 3 matrix, only 6 terms. If I had a 3 by 5 matrix, I'd have to do 15 of these. If there were a 7 by 10 matrix, there'd be 70 of these. It'd be crazy. Too many. It would be way too much. So I'm telling you, just go to that matrix menu, enter your matrix of observed values, and then go right to that chi-squared test in the calculator. All right. So let's see if they have any more to the problem here. I don't know if they do. I think that might have been it. Oh, then it asks for, okay, now what's the test statistic? All right, so there is a second part to this, which we see here on our calculator, 5.79. So the closest, now again, they're doing a lot of rounding, and you've seen this with other things. They're doing a lot of rounding. So the closest one to the actual 5.79 is 5.9 here. And you'll see when you read through the answer explanation, the reason they're getting 5.9 is because they did a lot of rounding. See, they rounded all the stuff to 1 decimal place. They rounded all those expected values to 1 decimal place. That's why it's a little off of what I'm seeing on the calculator. Okay. So if you entered 5.79, 5.8, I mean, that's not wrong. Well, let's see, this one was multiple choice, so not so bad. You just pick the closest one. 5.9 is the closest to 5.8. But yeah, what they're using is, they're using these rounded values, and that's why it's a little off. But it's still basically the same number. All right, so you're fine. Okay, so this was a long one, 40 minutes. A lot of introduction there to expected values in a contingency table, and this test for independence, calculating the test statistic. When I do videos after this, I'll just be using a calculator. All right, I'm telling you, it's going to be a lot easier just to type it, enter a matrix with those observed values, observed counts, and then go to the chi-squared test. All right. And I know it's going to be more accurate on the calculator than they're using here because they're rounding, but it's good enough. All right, it'll be close enough to where you'll be able to do these. All right, so hopefully watching me do this here on the calculator, write stuff out, watching, looking at more instruction when necessary, reading these answer explanations. I'm hoping all this stuff helps you when you do this on your own. And thanks for watching.